welcome to this problem walkthrough. Today, we'll dive into problem number 189, titled Rotate Array. In this problem, we explore how to efficiently rotate an array by a given number of steps. We'll analyze various approaches, discuss their trade-offs, and focus on implementing a robust solution. Let's get started. In this problem, we are given an integer array called nums and a non-negative integer k. The task is to rotate the array to the right by k steps. Rotating to the right means that each element is shifted one position to the right, and the last element wraps around to the beginning of the array. Now, let's talk about the input and output format. The input consists of two things: the nums array, which contains integers and has a size between 1 and 100,000, and the integer k, which can range from 0 to 100,000. The output is the same input array, modified in place to reflect the rotation. This means you must adjust the elements of the array directly, without using extra memory proportional to its size. To make this clearer, let's look at an example. If nums is 1, 2, 3, 4, 5, 6, 7, and k is 3, the output would be 5, 6, 7, 1, 2, 3, 4. The array has been rotated 3 steps to the right, with the last 3 elements wrapping around to the front. Here's the step-by-step explanation for the first example. Starting with the array 1, 2, 3, 4, 5, 6, 7, we rotated 1 step to the right. After this first step, the array becomes 7, 1, 2, 3, 4, 5, 6. Then, we rotated a second step, which gives us 6, 7, 1, 2, 3, 4, 5. Finally, after the third and last step, the array becomes 5, 6, 7, 1, 2, 3, 4. This is the desired output. Another example is when nums is -1, -100, 3, 99, and k is 2. After one rotation to the right, the array becomes 99, -1, -100, 3. Then, after the second step, the array becomes 3, 99, -1, -100. This is the final output after 2 rotations. Now, consider an edge case where nums is 1, 2, and k is 3. Here, the value of k is greater than the length of the array, which is 2. When this happens, rotating the array by k steps is equivalent to rotating it by k%n steps, where n is the length of the array. In this case, k%2 equals 1. So instead of rotating 3 times, we rotate the array by just 1 step to the right. After this single rotation, the array becomes 2, 1. This demonstrates how we handle situations where k exceeds the length of the array. The constraints make it clear that the length of nums will always be between 1 and 100,000, each element will be within the range of -2 to the power of 31 to 2 to the power of 31, 1, and k will always be non-negative, up to 100,000. To summarize, rotating an array means shifting its elements circularly to the right by k steps. The key detail is that the rotation wraps around, so the last elements of the array reappear at the beginning. The problem also specifies that the operation must be done in place. This means you cannot use additional memory proportional to the size of the input array, like creating a new array to store the result. If k is larger than the length of the array, the effective number of rotations is k%n, where n is the array's length. This insight allows us to handle large values of k efficiently without performing unnecessary rotations. Keeping these points in mind will help us design a solution that is both optimal and adheres to the problem's constraints. To start, let's consider the brute force approach. The intuition here is fairly straightforward. We rotate the array 1 step to the right, repeatedly, until we've done this k times. For each rotation, the last element of the array is removed and inserted at the beginning, while the rest of the elements are shifted to the right. Although this method is simple to implement, it has significant drawbacks. Its time complexity is k*n, since we perform k rotations, and each rotation involves shifting the entire array of size n. While it uses no extra space, making it an in-place solution, the inefficiency becomes a major issue for large values of k or n. This trade-off makes it impractical for scenarios with tight performance constraints. Now, let's move to an optimized approach that uses an extra array. Here, the key realization is that rotating the array k times is equivalent to repositioning the last k elements at the beginning. Instead of performing rotations one by one, we can directly construct a rotated array. First, we compute k equals k% to handle cases where k exceeds the array size. Then, we create a new array and copy the last k elements of the original array to its beginning, followed by the first n k elements to the remaining positions. Finally, we copy this new array back to the original one. This method reduces the time complexity to O(n), as we process the array only once, but it comes at the cost of O(n) extra space for the additional array. While this approach is much faster than the brute force method, its reliance on extra memory makes it less suitable when space efficiency is a priority. For a truly optimal solution, we can use the in-place reversal approach. This method eliminates the need for extra space by leveraging the properties of array reversal. The key insight is that rotating the array k times can be achieved by dividing it into 3 steps. First, reverse the entire array. This step effectively positions the last k elements at the front, but in reverse order. Next, reverse just the first k elements to restore their original order. Finally, reverse the remaining n k elements to fix their positions as well. Like before, we calculate k equals k% to handle cases where k exceeds n. The time complexity of this approach is O(n), because reversing sections of the array requires linear time, and it has a space complexity of O(1), since everything is done in place. These characteristics make it the most efficient solution. The in-place reversal approach stands out as the best strategy due to its optimal balance of time and space efficiency. Its key strength lies in reducing the problem to simple array manipulations using reversal, which eliminates unnecessary rotations and extra memory usage. The modular arithmetic, k%n, ensures that even for very large k, the solution remains efficient. This method is particularly useful in competitive programming and real-world scenarios, where performance is critical. While the algorithm is mathematically elegant, it does require a deeper understanding of array manipulation, which might make it less intuitive for beginners. However, once the concept of reversing parts of the array clicks, the approach becomes both practical and powerful. One trade-off of the in-place reversal approach is its slightly higher learning curve compared to the extra array method. Careful attention is required during implementation to avoid off-by-one errors when reversing sections of the array. Despite this, the approach remains the preferred solution as it combines the best aspects of performance and practicality. Its O(n) time complexity and O(1) space complexity make it well-suited for handling large arrays efficiently, and its ability to handle any value of k gracefully ensures robustness. Overall, this strategy represents the optimal balance for solving the rotate array problem. To understand the problem, we are given an array called nums with a size of n, and we need to rotate this array to the right by k steps. A rotation here means that the last k elements of the array will wrap around and appear at the front. To solve this, we first normalize k by calculating k equals k%n because rotating an array n times will result in the same array. Next, we perform the actual rotations. In the brute force approach, we handle one rotation at a time. During each rotation, we take the last element of the array, remove it using the pop operation, and insert it at the front using insert 0 element. Repeating this process 4k rotations ensures that the array is shifted correctly. This approach is simple to understand and implement, making it a good starting point for solving the problem, though it may not be the most efficient for larger inputs. In this approach, the key operations are removing the last element of the array and wrapping it around to the front. This ensures that the array maintains its correct order after each rotation. Let's walk through an example to see this in action. Suppose we have nums equals 1, 2, 3, 4, 5, and k equals 2. First, we normalize k by calculating k equals k%n, which gives 2% 5 equals 2. This means we need to perform exactly 2 rotations. For the first rotation, we remove the last element, 5, and insert it at the front. The array becomes 5, 1, 2, 3, 4. For the second rotation, we remove the last element, 4, and insert it at the front. The array becomes 4, 5, 1, 2, 3. After 2 rotations, the resulting array is 4, 5, 1, 2, 3, which matches the expected output. This step-by-step process shows how the brute force method works to achieve the desired rotation. Let's analyze the algorithm further by considering the data structures and key insights. The input and output are both arrays, and since we modify the array in place, an array is the most appropriate data structure for this problem. Now, looking at the time complexity, each pop operation is performed in O1 time because it simply removes the last element. However, the insert 0 element operation requires shifting all other elements one position to the right, which takes O(n) time. Since we repeat this process k times, the overall time complexity becomes O(k*(n). For the space complexity, the algorithm operates in place, so no additional space is needed beyond the input array, resulting in O1 space complexity. Additionally, it's important to account for edge cases. If k equals 0, the array remains unchanged. If k is greater than or equal to n, normalizing k ensures that we avoid unnecessary rotations. Finally, if the array has only one element, no rotation is required, as the array will remain the same. While the brute force method is straightforward and easy to implement, it becomes inefficient for large values of n and k due to its O(k*(n) time complexity. For better performance, we can use optimized approaches such as reversing segments of the array. This method involves reversing the entire array, then reversing the first k elements, and finally reversing the remaining elements. By doing so, the time complexity is reduced to O(n), which is significantly faster for larger inputs. However, the brute force approach remains a great starting point to grasp the mechanics of array rotations and is suitable for smaller inputs or scenarios where efficiency is not the primary concern. This implementation solves the problem of rotating an array to the right by k steps efficiently in place, with O(n) time complexity and O1 space complexity. We start by calculating k% equals n, where n is the length of the array, to minimize unnecessary rotations when k is greater than the array size. This operation ensures that the problem is reduced to rotating the array by k steps within its bounds. The three-step approach involves reversing segments of the array to achieve the desired rotation. 1. Reverse the entire array. By reversing the whole array, we effectively reposition the elements such that the last k elements become the first k elements, though in reverse order. 2. Reverse the first k elements. This step corrects the reversed order of the first k elements, making them appear in the original sequence. 3. Reverse the remaining elements. Similarly, this step corrects the order of the remaining portion of the array. For example, given nums equals 1, 2, 3, 4, 5, 6, 7, and k equals 3. After reversing the entire array and nums equals 7, 6, 5, 4, 3, 2, 1. After reversing the first k equals 3 elements, nums equals 5, 6, 7, 4, 3, 2, 1. After reversing the remaining elements, nums equals 5, 6, 7, 1, 2, 3, 4. This approach is optimal for in-place rotation, avoiding the need for auxiliary storage while maintaining clarity and efficiency. This is the Java implementation of LeetCode problem number 189, Rotate Array. The logic mirrors the provided Python solution, using the reverse method to handle the rotation efficiently in O(n) time. The array is reversed in 3 steps: the entire array, the first k elements, and the remaining elements. Key differences include explicit type declarations, the use of a helper method for reversing, and adherence to Java syntax and conventions. To solve the problem of rotating the array 1, 2, 3, 4, 5, 6, 7 by k equals 3, we start by initializing the given values. The input array is stored in nums, the number of rotation steps is k, and the length of the array is n. Since k can sometimes be larger than the array length, we calculate k% equals n to ensure k falls within a valid range. In this case, k remains 3 as 3% 7 equals 3. Now, we reverse the entire array, which changes it to 7, 6, 5, 4, 3, 2, 1. This reversal sets us up for the next steps. After that, we reverse the first k elements, which are 7, 6, 5. Reversing them gives 5, 6, 7, and the array updates to 5, 6, 7, 4, 3, 2, 1. Next, we reverse the remaining elements of the array, which are 4, 3, 2, 1. Reversing these gives 1, 2, 3, 4, and the final rotated array becomes 5, 6, 7, 1, 2, 3, 4. Moving on to a new example, we now consider rotating the array 1, 2, 3, 4 by k equals 6. We begin as before by initializing the input values. The array is stored in nums, the rotation steps are k equals 6, and the array length is n equals 4. Since k is greater than the length of the array, we compute k% equals n, which results in k equals 6% 4 equals 2. This ensures k is within the bounds of the array length. After determining the adjusted value of k, we proceed by reversing the entire array. Reversing 1, 2, 3, 4 results in 4, 3, 2, 1. Next, we reverse the first k elements, which are 4, 3. Reversing this subset gives 3, 4, and the array updates to 3, 4, 2, 1. Finally, we reverse the remaining elements, which are 2, 1. Reversing these gives 1, 2, and the final rotated array becomes 3, 4, 1, 2. Now, let's examine the case where the input array is 1, 2, and k equals 5. As usual, we start by initializing the values. The input array is nums equals 1, 2, the rotation steps are k equals 5, and the array length is n equals 2. Since k is greater than the length of the array, we compute k% equals n, resulting in k equals 5% 2 equals 1. This keeps the number of rotation steps manageable. Next, we reverse the entire array. Reversing 1, 2 gives 2, 1. After this, we reverse the first k elements, which is just 2. Since it consists of a single element, reversing it leaves it unchanged, so the array remains 2, 1. The final step is to reverse the remaining elements of the array, which in this case are 1. As with the first k elements, reversing a single element has no effect, so the array remains 2, 1. This gives us the final rotated array, 2, 1. By following this approach of reversing the entire array, then reversing the first k elements, and finally reversing the rest, we efficiently rotate the input array regardless of the value of k or the array size. To analyze the time complexity of our solution, let's break it down into its three main steps. First, we reverse the entire array. This involves swapping elements from the start and end, moving towards the middle, which takes n time for an array of size n. Next, we reverse the first k elements. Here, we perform k swaps, so this step has a time complexity of k. Lastly, we reverse the remaining nk elements, which requires nk swaps and therefore has a time complexity of nk. When we sum these up, the total time complexity is n plus k plus nk, which simplifies to 2n, and ultimately to n. This means the overall time complexity of the algorithm is linear, or n, where n is the size of the input array. Now let's consider the space complexity. The solution is designed to perform all operations in place, directly modifying the input array without using any additional data structures. The only extra memory used is for a few variables, such as n and k, which require constant space. This means the space complexity is 1, as it does not grow with the size of the input. Additionally, the best, average, and worst-case scenarios all share the same time complexity. In the best case, even if no rotation is needed, such as when k equals 0, the algorithm still performs the same steps, resulting in n. For the average case, with arbitrary values of k, the time complexity remains n. Finally, in the worst case, where k is very large, the algorithm efficiently reduces k to k% n before proceeding. This ensures that the time complexity stays n, regardless of the value of k. Let's compare this approach to a brute force method. A naive solution would involve rotating the array one step at a time, repeating this process k times. Each rotation requires shifting all n elements, resulting in a time complexity of k*n. For large values of k, this becomes extremely inefficient. In contrast, the current approach leverages the reverse method, reducing the time complexity to n, no matter the value of k. This makes it far more efficient, particularly for large arrays or high values of k. To mathematically prove this, note that the reverse operation is linear, as each element is visited once during a reversal. Since we perform 3 reversals on disjoint sections of the array, first the whole array, then the first k elements, and finally the last nk elements, the total operations are proportional to the size of the array, n. This keeps the time complexity at n. With no additional data structures, the space complexity remains O1. By using the reverse method, the algorithm achieves optimal performance, both in time and space, for this problem. When working on the rotate array problem, there are a few common mistakes that can trip you up. One is misunderstanding the rotation logic itself. A lot of beginners confuse rotating to the right with rotating to the left, or fail to realize that rotating an array by its length or any multiple of its length results in no change. This can be resolved by always calculating the effective rotation using k equals k% before proceeding. Another frequent pitfall is neglecting edge cases, like when k is 0, k is a multiple of n, or the array is empty. These situations might lead to unnecessary operations or even runtime errors, so it's important to handle them explicitly up front. Lastly, some solutions rely on brute force, rotating the array one step at a time for k steps. While this might work, it's inefficient, with a time complexity of O(n*k). Instead, you should aim to use optimized techniques, such as the reversal algorithm or an auxiliary array, to achieve linear time complexity. Another mistake to watch out for is incorrect implementation of the in-place reversal method. This approach involves three distinct steps: reversing the entire array, reversing the first k elements, and then reversing the rest of the array. Errors often arise from reversing the wrong subarrays or mismanaging indices during these steps, so careful attention to the boundaries is key. Additionally, some solutions unnecessarily use extra space when an in-place solution is more appropriate. For example, relying on an auxiliary array when the task specifies constant space increases the space complexity to O(n). To address this, methods like the reversal algorithm or cyclic replacement should be used when space efficiency is a priority. In an interview setting, it's important to focus on optimization. Interviewers typically value solutions that improve from a brute force O(n*k) approach to an O(n) solution, as this demonstrates your ability to optimize and think critically. They also pay close attention to how you handle edge cases. For instance, you should be ready to address scenarios like k being 0, negative, or larger than the array size. This shows a thorough understanding of the problem. If you choose a simpler approach, such as using an auxiliary array, make sure you explain the trade-offs you're making, particularly the increased space complexity. Finally, this problem introduces key patterns like modular arithmetic and array manipulation, which are common in other rotation or cyclic problems, so recognizing and leveraging these concepts can give you an edge. This problem is closely related to a few others on LeetCode. For example, LeetCode 61, Rotate List, involves similar logic but applies it to linked lists instead of arrays. Another related problem is LeetCode 396, Rotate Function, where the task is to compute the maximum value of a rotation function. Additionally, LeetCode 48, Rotate Image, deals with rotating a 2D matrix by 90 degrees, which requires similar modular arithmetic and in-place techniques. Exploring these problems can help you identify common patterns and broaden your understanding of rotation-based challenges. There are several approaches to solving the rotate array problem, each with its own trade-offs. The reversal algorithm is one of the most efficient methods, involving three steps: reversing the entire array, reversing the first k elements, and reversing the remaining elements. This achieves O(n) time complexity and O(1) space complexity. Another option is to use an auxiliary array, where you copy elements to their rotated positions in a new array and then overwrite the original. While simple, this approach increases space complexity to O(n). Cyclic replacement is another efficient method that swaps elements directly to their correct positions in a cyclic manner, maintaining O(1) space complexity. However, it requires careful tracking of visited indices. Lastly, if you're using Python, slicing provides a language-specific shortcut for rotating arrays in one line, though it comes with an O(n) space complexity due to creating a new array. Each method has its strengths, so choosing the right one depends on the constraints and requirements of the problem. Great job! To summarize, we explored different strategies to solve the rotate array problem, focusing on efficiency and edge case handling. Remember the importance of choosing the right approach for the given constraints. Thank you for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!